Actually, talking about speed, we now move our attention to the so-called offline optimization, which can be shown to give the optimal solution faster compared to implicit optimization if we do lots of pre-processing offline, meaning we prepare the solution in advance for all possible initial conditions, and then we just need to implement that solution. So what offline optimization is that it applies so-called parametric optimization to solve quadratic programs with parametric right-hand side. So what we have done now is we have separated again the initial condition for our quadratic program into a separate term. So we have a fixed right-hand side, but we have a variable term here which depends on some parameter. And in model predictive control, this parameter would be exactly that initial condition which initializes our optimal control problem. And then our objective becomes to find the analytical solution to this parametric quadratic program. And you can think here LQR control on steroids, because LQR is also an analytical solution to an optimization control, optimal control problem, right? We have a cost function that we want to minimize, which is a quadratic cost function. We have linear constraints in form of equality prediction model, like linear prediction model, but we don't have any inequality bounds on the states and on the inputs. That would be in the LQR case. And still, despite having basically an equality constraint quadratic program, in LQR case we can find an analytical solution. That's point number one. And point number two, the solution has a very nice structure. It is a linear function of our parameter. And something similar can also be done if we consider constraints in the QP settings. So we have also inequality constraints here. So what we do in the offline optimization is that we offline determine the optimal analytical solution to a given problem. So we find for a function of which determines the primal optimizer as a function of these parameters which enter the cost function and the right-hand side of the constraints. We determine this function. Actually, doing that is very difficult. But once we find this function, what we need to do online to find the optimal control inputs is just to evaluate this function. And here, yes, I'm oversimplifying, because by saying just to evaluate a function without telling you what the function really is not really meaningful. But fortunately for us, it can be shown that at least for parametric quadratic programs which originate from standard model predictive control, this analytical representation of the primal optimizer has a form of a piecewise affine function over polyhedral critical regions. That means that we partition our state space into polyhedral regions. So each of these green pieces, and there are also blue ones and the red ones here, they are polyhedra, meaning convex objects defined by linear inequalities. They are captured here. And in each piece of that state space region, we have an affine feedback law which is defined over these regions. So the analytical solution is a piecewise affine function. It's actually more than that. It's a continuous piecewise affine function. And you might wonder how come we started with a quadratic program with a quadratic objective and we ended up with an affine or piecewise affine feedback law. So is there some kind of quantization involved, or is this an approximate solution? No. This is exactly the same solution numerically wise that we would obtain, for instance, using the active set method, for exactly the same argument why LQR leads a linear optimal feedback law. Because you take the gradient of the objective function, which is quadratic. Well, the objective function is quadratic and the linear is gradient, and you express the optimal control input from that. So this is the exact analytical solution to a parametric quadratic program. It takes a form of a piecewise affine function, and so far it's good. The bad thing about this is that to construct this function is actually very difficult. Why? Because offline optimization is actually the other side of the same coin, where the online optimization is on the other side. Remember, in active set method, what we were doing is, for a particular right-hand side, we were determining which active set is optimal for that one right-hand side. Now imagine that you allow your right-hand side of your constraints to change. Basically, you say, I don't know now where my right-hand side will be. Can you please give me the solution for all possible right-hand sides? Well, this also means that in the worst case, we will cover all possible combinations of active constraints, right? And this is exactly how the solution is constructed. So we explore which active sets can be possibly optimal for some right-hand side parameters. And then for each right-hand side, we do it exactly as we did in the active set method, except instead of solving the problem numerically, because the right-hand side in the active set method was fixed, so we could compute the numerical value of the primal optimizer. Now we just let the right-hand side to be like a symbol, an unknown variable. So we have to find the solution with respect to this theta. And actually using symbolic algebra, you can find out what should be the representation of this matrix capital K and this vector small k, such that it exactly solves the Karush-Kuhn-Tucker conditions for some region around your selected right-hand side. And it turns out that if we now take this primal optimizer and also the dual optimizer, we plug it back into the original primal and dual feasibility constraints, then we also obtain the critical region as a polyhedron. So the bottom line is, if you fix your right-hand side, you will obtain basically an affine local feedback law. If you don't move it too far away, the same feedback law will stay active. Once you move too far away, we have to switch to a different feedback law, which comes from a different active set. And this is actually what makes the construction of this analytical solution so difficult, because we have to prepare, we have to compute all these regions for all possible values of the right-hand side. But I mean, you get what you ask for, right? You don't know what your problem will be? I will give you the solution for all possible problems. So by exploring all possible active sets and doing some clever linear algebra, we can find out what should the properties of the piecewise affine feedback law or the optimizer be. The good point is, despite this being tremendously difficult, this is done offline before you start even using the solution on your hardware. Because then once we have the solution in form of a piecewise affine table or piecewise affine function, it's basically a lookup table. We need to find out which of these regions contains particular measurement of our parameter. Again, that's the state estimate which comes online. So among all those regions, we determine which of them contains our measurement, and then we just apply the corresponding feedback law. That's why I say, I mean, it's easy. It's not that easy, because it takes space. First, we need to store all those regions in the control hardware, and it also takes time to find which of the regions is currently active for a particular measurement. Okay? Still, I would claim that for large or for certain class of problems, it's about the speed where this accelerates over the active set method, because notice that at this point we are just basically checking linear inequalities. We are not doing any matrix inversions, nothing like that. So I would claim we save on the computational effort because we do simpler mathematics online, but we certainly lose on the storage because we need to store all those critical regions in the memory of the control hardware. So we are trading off, yeah?
What is the number of critical regions and how is it related to the number of possible...
I have that just on the next slide, so if you allow me, I will show it next. Okay, but to this one, where we gain, and this is really a huge gain, if we want to address, if we ever dream of using MPC on platforms where such kind of optimization-based strategies were unthinkable before, like programmable logic controllers, which are often used in practice. It's about simplicity of the implementation. There are no iterations, because these iterations, you never know what your upper limit will be. Well, we do know that was those 100 billion iterations. So if you are developing a safety critical control system, you are obliged to design your hardware which is capable enough to accommodate your worst case, right? While with this kind of solutions, we do know, I mean, it's difficult to compute the regions, but once we do that, we know exactly how many of them we have. So we know exactly in the worst case how many to a single floating point operation, how much computational effort will we need to implement the controller? And the bound is exact compared to those inexact bounds for, say, active set methods. So we gain on some guarantees that we get on how much memory we will need and how much time we will need to implement these solutions. But even more importantly, I would say, is the simplicity of the implementation. There are only additions, multiplications, and comparisons involved. No, not even matrix divisions. There are no divisions at all involved in implementing this control strategy. So it might be a viable way to go when we are targeting really simple hardware. And to your question, how many? Well, many. In the worst case, as many as there are total number of combinations of active constraints, those 100 billion. But you see, that's why I'm saying it's really the two sides of the same coin. You could construct an QP problem where the active set method would need to go through all possible combinations anyhow. So if you are so unlucky that you run into this kind of problem, that offline optimization gives you like 100 billion regions, it might very well be that also your active set algorithm will have to perform 100 billion iterations. Okay, so at least that analytical solution gave you an indication. Okay, let me put it this way. You don't even have to use the analytical solution because it might be too complex, too many regions, too much space that it takes on your control hardware. But it gives you an indication of the complexity of the problem you are solving. Like how many iterations will the active set method take in the worst case. So there might be that stupid little example that I show you, 60 constraints, 5 variables, 100 billion would be the upper bound. The practical number of regions would be probably 100. That pretty much says that also the online active set method would only need up to 100 iterations. But without seeing the analytical solution, you couldn't make this argument about the online active set methods. That's my argument. So these kind of solutions, they are also very useful in analyzing properties of the optimization problem, like how complex is it? How complex are the relations between the optimization variables and the constraints? Okay? So basically, the number of critical regions is determined by the complexity of the problem. Yes, this tends to be large, but you simply got what you asked for. It's like you got a formula for all possible realizations of your right-hand sides in your optimization problem. Of course, if you ask for the full solution and they say, you know, I just spent 10 hours computing the solution, but I'm just going to only use a small piece of my, say, initial conditions. I'm not going to run into some initial conditions that are far away. Then why did you construct the solution without this knowledge? So my point being, here we have to bound the exploration space as to get a solution which is of reasonable size. Okay? And there are many theoretical algorithms and also practical ones that can keep this complexity under control. Now, this is not the most important topic of this summer school, because I would even advocate that if you can choose your control hardware that can fit an online active set method or some other kind of online optimization algorithm, you should definitely go that way. Because you get very efficient numerical algorithm, but the most important distinction between online and offline is that in the online approach, we are free to change, say, the Hessian, the constraints, and so on, kind of on the fly, because we are repetitively solving the problem again and again at every sampling instant. With offline optimization, the Hessian and the constraints, they have to be fixed, so like set in stone. That means you have zero flexibility in changing your MPC setup on the fly. That's a huge disadvantage of these methods. So if you have enough hardware resources, definitely go the online way. However, and I will show it just in a second, if we come to, say, programmable logic controllers, and you will see that after just half an hour, you will not just forget about online optimization, you will forget about any optimization at all running on that type of hardware. These kind of solutions are pretty much the only option to go when it comes to really dumb hardware. So that would be my argument. Yep.
You said that you restrict your exploration space.
Mm-hmm.
So you don't consider all possible cases of the initial condition, but only a subset, right?
Precisely that, yes.
So what happens in practice if you encounter a value which is outside of this set?
I would use the same argument as saying your boundary of the exploration space should definitely cover your state constraints, at least. Mm-hmm. But what I'm saying even then is that how realistic even in practice is it that you will start your plan from a particular combination which is clearly contradictory, say, to your control device? Like I will use like a chemical reactor to my advantage, okay? Usually when we increase the temperature, also the concentration of the product increases and so on. So probably it is not realistic to start from a high concentration and a low temperature, because such a scenario is simply not realistic in practice. Mathematics allows this combination, but it's simply not a physically realizable starting point. That's what I'm saying, that sometimes we can use this reality to our advantage to kind of limit the exploration space.
So this means that you limit yourself to the values which kind of make sense from the physical point of view.
Precisely that. Because yeah, go ahead.
But if this space is still large enough and produces a huge number of how is it called? Regions,
yeah.
What do you do then?
Then you think twice whether going the analytical direction was the best one. Really, the analytical solution is usually applied when you have no other option. No other option could mean that you have nanoseconds to compute your control action, for instance, where even the best online algorithms wouldn't work. They work like in microsecond range, something like that. If you have nanoseconds, you cannot allow any complex algebra. There you are really limited to comparisons, additions, multiplications, and that's it. Or where you have, and again, I'm just referring to what will come next. If you have a programming language that imposes such restrictions on you that A plus B is pretty much the complex mass, most complex mass you can do on that type of device. So those would be the situations where you would go this direction. Okay? Good. Yeah, no problem.
Like a stupid idea. So maybe this approach then is also suitable for like analog implementation.
Precisely that. Yes, it can be done. The implementation can be done in a completely analog fashion, like operating amplifiers and these kind of things. Yes, you can completely avoid digital mathematics. That's one of the. Having said that, there are even variants of the kind of the active set method that also runs completely in digital. Francesco Borelli from UC Berkeley has developed these kind of algorithms. And yeah, I mean, it's truly amazing that you can synthesize an electric circuit where the optimum of the voltage is the optimal solution to some kind of optimization problem. So then you just pick up your resistors, capacitors, you put them together, no digital algebra involved whatsoever, and suddenly the circuit converges in nanoseconds to the optimal solution. Of course, there are other problems because then it's very sensitive to noise, but it's a very promising direction. And yes, I mean, this would be even simpler to implement in a complete analog fashion. Yes, I agree. I mean, don't forget that the original PI controllers, they were implemented in a pure analogic way. Okay, there was no mass involved like on the computational platform. So yes, there is certainly promise here. I just wanted to point out we have two approaches, and this is one of them, because I saw that this is something we might do at least for some of the projects, like taking these kind of solutions and implementing them, say, on Arduino. We have that running on Arduino without troubles because they're so simple that even Arduino can do that. But even more dumber hardware than Arduino can implement these kind of solutions. Okay? So what I just want you to take away from the offline optimization direction is that parametric optimization is an active set method, but it's prepared for all options, for all possible realizations of the right-hand side. So whichever advance people ever make to the active set method, like improving performance and so on, that can be applied to this parametric optimization as well. That's the first takeaway. And the second takeaway is what I was describing. Sometimes our hardware simply does not allow anything beyond additions, multiplications, and comparisons. If you are forced, or if you do see benefits of running mode operative control on that type of a platform, and you cannot change the platform, then this is again the viable option to go. But as I realized, for the FPGA modules, you will do online optimization. For Arduino, you will use online optimization. We will see how far we will get in the PLC module. Okay? So this is certainly not the most important cornerstone of this summer school, but I will be more than happy to discuss that in the details, because that's basically what I do in my research, this parametric optimization. Okay? So to sum up this first part, the dumber the hardware, the simpler the control policy has to be. And just in the next presentation, I want to show that there is really hardware which is really dumb in terms of what it can do. And the most dumb type of control hardware you can encounter are programmable logic controllers. Just for my information, could you please raise your hand if you have ever worked or at least have seen a programmable logic controller in your life before? To get an idea. Okay, how many of you have programmed programmable logic controllers? Okay, good. So 5 or so. Good, perfect. Because I'm going to do a fast introduction into PLCs anyhow, because it is my belief that unless you are exposed to how limited this hardware really is, I mean, it kind of keeps you on the ground with your scientific discrepancy from the reality. Like I was saying, like, oh, but I can do everything on my computer. But then you come with that solution to your boss and he says, okay, so let's get it running on the hardware which is already there. And you say, what? I mean, PLC? No, it will not work. Okay. And as I said, maybe you can convince him to use a new hardware, but most probably not. What's most frequently used control hardware is on the planet are programmable logic controllers. I just call them gray boxes. Okay? There are some which are green, some are orange, but most of them are gray. That's really the distinctive point. And what they really are, they are generalization of two kind of historical breakthrough when it came to, well, control theory and also computing in general. The first one was relay. Okay, we all know how a relay operates. We have a coil which we energize by closing this switch, and the coil then attracts this contractor and it then powers the load. Okay, that's exactly what it does, and it was doing it historically to reconstruct signals transmitted over long distance. But then, of course, the question is, okay, so this relay is great in operating some kind of device in an on-off manner, because that's precisely what programmable logic controllers do. They mostly deal with binary logic. So we have something to operate a load, but we would like to have something more complex as a switching logic compared to just a manual push button or a switch or something like that. Ideally, we would like to have to implement more complex switching conditions, right? And this is where the second breakthrough in the history came along. Do you know what it is? Transistor. That's a transistor, exactly. That's a reconstruction of the very first transistor, quite huge thing. I'm not an expert in the electrical field, okay, so I will just resort to these slides. Basically, by combining resistors and transistors, we can realize various rules from the Boolean algebra. So if we connect transistors in a serial fashion, then we obtain a logic multiplication between two logic conditions. If we connect them parallelly, then we obtain a logic summation according to the, well, with the associated truth tables. Okay? And what PLCs have then done is that they have combined these kind of logic rules with the physical switching to operate a plant according to some logical schedule. And even better, they made these transistors to be like software configured. They didn't have to be soiled to the ground mechanically, but you could, by means of a program, change the arrangement of these logic rules. And this then gave rise to various gates. And what we do in logic or in the programming of PLCs is that we develop a program which consists of these basic logic gates as to reflect some logic operation of the device. So PLCs are really about the logic. They are around already for quite some time. The first one was developed in 1968. And since then, they are everywhere. I mean, especially in the process industries, I mean, they form something like 90% of all the control hardware, which is on the site. So very, very good. I mean, just enter an elevator. If you would open one of those panels, you would find a PLC inside. So PLCs really, they are everywhere. And what they are really electronic replacement of electromechanical relay controls. So they have, they have a power unit, they have a CPU where we store the program, but they have also input-output blocks to which we can directly plug in, say, the digital inputs and outputs, analog inputs and outputs that are then switched by those physical relays as to reflect some input event to propagate to the output via certain logic conditions. They are solid state on two levels. First, there are really no physical relays in there, but there are just solid state based. And also the overall construction is completely solid in terms, it doesn't have any moving parts. So there are no fans inside of these devices, for instance. Which also means that they are very, very attractive for process industries. And why are we talking about them here is that they really represent the most common denominator when it comes to implementation of control strategies. In other words, if you want to develop a control strategy that you want to run everywhere, it has, in the first place, have to run on PLCs. And PLCs have really draconic limitations on the memory. We are talking kilobytes of memory that we have available. We are talking about CPUs, which are equivalent to Intel processors from the previous century. And they have programming capabilities, which basically means we have to program them using a kind of assembly language. So these are really such severe limitations that really you would be lucky enough if you can get LQR running on these controllers and not MPC or something like that. Yeah?
You previously said that this PLC is a bunch of logical units, right?
Which are completely software-based nowadays.
Okay, so the processor basically emulates these logical units.
Precisely that, yeah, exactly that. So everything runs on the CPU. There is no hardware configuration. Unlike FPGAs, where you let the program basically synthesize your board, your hardware board, here everything runs in a software fashion, but internally it works pretty much according to those logic rules. Okay? So internally these PLCs, they are just a bunch of individual modules connected. We have input and output interface, and basically what makes PLC so attractive for the industries is that you just take your standard sensor, which has some voltage or some current output, and you just plug it into the plug of the PLC. There is no need to have like a USB port, a protocol, a driver, nothing like that. There are simply standardized voltage and current signals, so you can just take any standard accessory from your catalog and just plug it into the PLC and it will work. Okay? So when it comes to inputs and outputs, we basically classify them into two groups. We might have digital or analog inputs and outputs. The digital inputs and outputs, usually they are either voltage-based or current-based. What makes PLCs very interesting is that they use decoupling between the physical layer to which we connect the sensors and actuators to, and the CPU board which processes those signals. And this isolation is usually done either in a galvanic fashion for high-speed communication, or it can be done by optocouplers where you do a complete separation of the two electrical circuits. So it makes your CPU basically non-destroyable by some external say some kind of electrical disturbance that might happen on the cables which lead, which connect the PLC to your sensors and to your actuators. And this isolation can be implemented both for inputs as well as outputs. Then we have analog signals that we can process, both inputs and outputs. These are usually either voltage-based or current-based. What makes, again, this a little bit interesting is that usually in PLCs we use something which is called the elevated zero. Like you want to distinguish a situation where your, say, sensor is off versus from the situation where there is a physical kind of break on the communication link between your control hardware and the sensor. Okay? So the zero signal from the sensor would be represented by, say, 4 milliamperes, while if there is less than 4 milliamperes, you know that you have a problem on the communication line. Okay? So we can use voltage or the current signals, and what makes actually analog processing so difficult and so also challenging for control design is that we always have to use quantization. So when we do analog to digital conversion, then we know that we have only a certain number of bits available to actually translate the analog value to digital information. And if the encoder is not precise enough, like here we are only using 3 bits, that means we can encode 8 levels. This can pose additional challenges already on the level of the control design, because suddenly instead of a continuous value, your control algorithm receives basically quantized control inputs. And if it is not designed with respect to those quantized inputs, its performance might be bad. Even though you tune everything perfectly on simulations, suddenly you just include quantization and it completely destroys the control performance. So I'm just mentioning these kind of issues to you, just to know that it's not just about the control design. It's all these little things which then influence both the program complexity but also the quality of the control algorithm. Then we have memory, where we store everything. And again, I just basically, it's not my intention, but it will turn out that what I'm doing is I am making you less and less interested in PLCs. Because I'm telling you that you have to deal with stuff which you don't really want to deal with, like quantization. Let's deal with another stuff. What do you do in standard programming language where you want to use a variable, like in C? What do we have to do? We have to declare the variable, right? Declaring a variable means assigning a symbolic label to it, but also specifying its data type. Should it be an integer? Should it be a float? These kind of things. In PLC, it's usually even worse. You have to even specify the location in the memory where you want to store that variable. And it's up to you to make sure that 2 variables do not overlap in the memory. Of course, there are some advanced PLCs which do this memory allocation for you automatically. But again, I just want to show you the common denominator. And then the standard practice is we do even the stupid memory allocation we do manually.
So before you said that PLC is a bunch of logical units.
That's true.
You talk about variables. So where do variables come from?
They come from the combination of logic with floating point arithmetics, which can be a part of programmable logic controllers. So traditionally, yes, PLCs were exclusively about logic. Then people realized they are very versatile type of hardware, so they added capability to process also floating point mass. And for that, you need to start working with these kind of variables.
So there are like type of blocks which take not logical inputs, but number.
Yeah, or it can be some internal variable of your control algorithm, for instance.
Can you really write a program for a PLC, or you only need to specify the blocks and connection?
You can do both, and I will show how we can do that. Yes. Okay. So it's not just about the allocation. This is probably the most important slide of my whole presentation. Okay. This single bullet. The most simple, which means also the most abundant PLCs in practice, they have something like 2 to 8 kilobytes of memory available. Just think of what you can do in 2 kilobytes. Can you write a hello world program in C and look at the size of the binary? Will it be under 2 kilobytes? I'm not that certain about it. It might, but okay, we are talking hello world program. Here we are talking about implementing some decent control algorithm, and it can very well happen that we have 2 kilobytes of memory available. Okay? So really, PLCs are about having limited memory. That's the first thing. And this memory is separated into 3 levels. There is a load memory where we store the program. There is a work memory where the program stores its variables. And then there is a so-called retentive memory, because if the power for any reason goes down, then PLC is able to at least store certain values in this retentive memory, and then on a power up, it restores those variables in the control algorithm. So it has battery backups and everything like this. And as I said, traditionally, PLCs require manual allocation of the memory, which means that first of all, we have to find what's the appropriate data type. And we can talk bits, we can talk bytes, words or double words, and the double words can both mean long integers as well as floating point numbers in the single precision arrangement. And we have to find the location for them in the memory. And finding the location basically means finding an address that we associate with particular variable in the memory. And this address, it's composed of whether we are talking about a variable which corresponds to the inputs or the outputs or some internal variable. We have to specify the size and the address. So long story short, what we have in the PLCs, say with 2 kilobytes of memory, is we have 2048 bytes. And if I want to store a short integer, meaning an 8-bit number, I give it an address VB0. What this means is that we are going to the internal memory, we are allocating a space for a byte, and we are placing it in the memory table on byte number 0. Say my control algorithm then needs a longer integer, a 2-byte integer, so 16 bits. I have to find a place for that. I cannot use this slot because it was already occupied by some other variable. So I have to find which of them is the first 3, and I have to put this physical address next to my declaration of that variable. For 4-byte variables, we need to allocate 4 rows and so on. Of course, the common practice is that then you do this nice allocation, and then you say, oh, but maybe I don't need this variable at all, so I will remove it. But then you say, but I need another 4-byte variable. But you cannot store it already here. You will need to find a place for that. So the bottom line is, just planning for the memory allocation is almost as important as writing the program for PLCs. And we all know that it's a very good practice to think before we write a program, right? That's what I was always told, and I always violate this principle. I first program and then think about the program. It's a perfect recipe for disasters on PLCs. You literally have to have your program designed before you start programming it into PLCs. Otherwise, you will end up with a memory table which is full of holes. So there is plenty of space, but nothing really fits in those tiny areas. So we have to reschedule everything. And we have to do something similar for bits. So just the takeaway note. There are PLCs, many of them, which require manual allocation of the memory. Keep this in mind if you ever are forced for any reason to work with PLCs. Okay? And then we come to the processor which performs the program. It basically scans what the inputs are, the physical inputs connected to the PLC. It executes the program and writes the corresponding outputs to, well, the output value. It writes them to the analog and digital outputs, which basically mean it energizes or de-energizes the coils which are responsible for making the physical connection between the power source and your actuated device. And then there is also some housekeeping which takes place. Again, a takeaway. There is a fixed allocated time, and if your program for any reason takes too much time, it just gets killed, no questions asked. So implementing something on PLC is basically a safety critical program that you have to really make sure that it fits inside the scan rate of your CPU. Of course, the slower the CPU is, the smaller this scan rate is. And then finally, we can maybe fire up the PLC and it will work. I mean, these are just little details. What I would like to come is exactly of how we program these things. And how should we do it with the launch now? I mean, we have 1.5 hours allocated for the launch. I believe most of you opted for the launch here. Even if you didn't, I believe 1 hour for the launch should be enough. If you would allow me, I would still use this half an hour until 12:30 for the lecture, and then we go for lunch. And we are never precisely back anyhow, so there will be delay when we start. So I hope it compensates somehow. Okay? Are there any objections? I mean, you are the bosses here. I'm just the one who is delivering the lecture. Okay, no, I take it as no objections. Okay, so let us continue with this excursion into PLCs. And if you didn't think that maybe quantization is bad, if you still were not turned away by manual memory allocation, maybe you will be turned away by the way how we program this kind of device. But trust me, it pays out if you can get something running on PLCs. You have the largest market possible for your controller. Because really, PLCs are like 90% of all industrial control systems. If you can get them run on PLCs, you are covering everybody. That means money. Okay, so we have basically 4 types of programming languages, 2 of them being purely graphical ones and 2 of them being purely textual. And all of them are basically assembly languages, meaning you have an instruction like add 2 numbers, and then you provide the operands like which 2 numbers you want to add, and the value is stored somewhere, and maybe propagate it along the program flow. And all of them are extremely simple. That means you can say bye-bye to any complex algorithm. Complex, I mean really anything beyond LQR, and maybe very simple of those analytical solutions. However, there are some PLCs that do support, say, C code programming, where you could use these algorithms, but in general, no. I mean, even anything beyond simple floating point mass like division, maybe square root is the pinnacle of what PLCs can do. Basically, we have to restrict and keep our algorithms to be very simple. If you invest more money, and it's not the control designer who invests, it's the operator of the control system which decides. If for any reason he is nice enough to you, he buys up more elaborate hardware, maybe you can get C running, maybe you can take your active set methods. Yes, there are PLCs like that, but then I wouldn't even call them PLCs, they are just industrial PCs. Okay, so by PLC I really mean something like 8 kilobytes of memory programmed using these pesky languages. That's how things are done. Okay, so let's dwell immediately into those 2 graphical languages. That's what I want to cover today. The first one is so-called ladder diagrams. They are called a ladder for a reason. If you would rotate this figure 90 degrees anti-clockwise, you would find that it kind of resembles a ladder where basically the current tries to climb all the way to the output. So this Y here is the output, say a bulb or a light in this room, and this might be switches which prevent the current to flow all the way to the light. Okay? And if you make the switches close for the current to flow, then the output will be enabled. If those switches open, then the flow of current is aborted and the light goes off. Okay? So these ladder diagrams, they are one-to-one equivalents of electric wiring diagrams. And they consist of 5 basic building blocks. The first one is there is a power source here. It's a kind of a bus. It's just a graphical element of the language, but it still has a meaning. Okay? Then we have blocks which do represent contacts, and we have 2 types of these contacts. This we call a normally open contact. So it's a binary kind of a push button, which is normally open and it can close. And this one is normally closed, and so if there is no power, it's closed. If there is power, it's open. Okay? Then we have the output coil, which energizes the control device. And then we have junctions, which later on will allow us to form a more complex switching logic. Okay? And if you ever wondered why these blocks are exactly in this shape, well, that's because historically, these ladder diagrams, they were designed in purely text mode. I mean, the first PLC was from the 1968. I mean, when was Windows when it came around? It was 1990, something like that. In between, I mean, the people didn't wait. They used just a pure text mode for that. So that's why the blocks, they look like that. Okay? So it's now all about how should we combine together those basic building blocks as to represent logic which we require. So let me just give you an example. You have a machine, say some kind of drilling machine, and you are only allowed to start up the machine when the gate is closed and maybe when some safety switch is turned on, just to make sure that it's safe to enable the machine. Okay? So obviously we would use a binary multiplication because we want only to enable the machine when the gate is closed and when that safety switch is enabled. Okay? And of course electrically we can realize it like this, but the power of PLCs is that this is really freely reconfigurable. So we can as well graphically assemble more elaborate switching conditions, like if we put them in parallel, then we suddenly have the Boolean summation of those two inputs. So switch on the machine, either if the gate is closed or when the safety switch is on, something along those lines. Okay? And of course, it doesn't end up with those kind of simple and or arrangements. We can put them together, right? So it should be pretty straightforward to encode this Boolean algebra using those basic blocks, right? So we have, remember, whenever we have Boolean multiplication, it's a serial arrangement of contacts. And if we have Boolean summation, it's a parallel arrangement. So here in this case, we have two parallel branches for the current to flow. And on the first parallel branch here, we have a series arrangement of A and B, putting aside what A and B mean. They are just binary events, on and off, okay? Nothing else. And in the second parallel branch, we have just the C. Okay? We can take something more complex when where this symbol here denotes the negation. So this normally closed contact, it would just look like this. Okay? So then developing a logic, a control logic, basically means translating these kind of written Boolean statements into these ladder diagrams. That's what we do. First, we have to design those logic rules, but we also have to translate them into the PLC, and we can do that via these ladder diagrams. And then, of course, we can have anything more complex, so let's just make sure that we know how to, for instance, read those diagrams. So here we have the normally closed contact, so that's just the negation of D. Then there is a junction, and whenever there is a junction, there is a Boolean plus. Then the second parallel one is E, plus the negation of F. The whole thing is then multiplied by C. Of course, certain rules similar to traditional algebra, they also apply to the Boolean algebra. So logic multiplication takes precedence over Boolean summation. Okay, that's why we have to put the parentheses here. The whole thing is then multiplied by the negation of B, and voila, we have the formula. Okay, let me now pose you the following question. Let me assume these two ladder diagrams, and this is the corresponding logic formula which drives the inputs based on 4 events, A, B, C, D, and is another formula based on just 2 inputs. And I'm asking, aren't these 2 diagrams by any chance equivalent? Okay. Okay, the straight answer would be no, because one is more complex than the other one. But the more elaborate answer would be, well, let's check, because if they would be, it would have great benefits, right? Instead of 4 sensors, like binary sensors, we only need 2 of them. That means a cheaper implementation of the control system. And it's also, this program consumes less memory. I mean, you can argue whether 2 blocks versus 8 or 9 is a big difference. It is. For a PLC with 2 kilobytes of memory, it makes a hell of a lot of difference, because each of these blocks, again, needs to be stored in the memory. And we also get easier maintenance of the code. I mean, if you look at this 1 year from now, maybe before you had a clear idea what it represents, but this is certainly easier. And I would claim they are equivalent. And yeah?
They might be not equivalent if it is implemented like real physical switches. The switches don't switch at exactly the same time.
That's what I said, how the program is executed in the PLC. First, the status of all inputs is read, okay, into the memory. So the physical inputs, those values are stored in the memory, and they are kept constant during the execution of the entire program. So I guess what you mean is that when one input would influence the other one, then kind of you can get like a non-deterministic behavior of the system, something along those lines. But here it's really that those values of these inputs, they are fixed. Whenever they are read into the PLC to execute the program, their values are fixed. So there is no kind of influence of these sensors to each other.
I was talking just about the race conditions.
Might be, but again, this is fixed by keeping everything constant at the start of the program loop. Okay. Okay. So, okay. How can we prove that they are equivalent? Okay. There is, of course, an engineering approach that I like very much. Like, okay, let's explore. Okay. And you might find something really strange, for instance, here. Like, okay, so we have a B here, we have a negation of B in a parallel branch. Okay, so what this means is that, what does it mean? Does it mean anything?
B can be closed or open.
Yeah. In other words, this branch here, it doesn't really depend on B, right? Because if B is closed, it will flow like here. If B is not closed, it will flow like that, provided A is closed. Okay? So it kind of indicates that we can eliminate B from the diagram. And we can do some similar engineering like reasoning. But of course, I mean, come on, we are at the university here, right? And what I'm actually trying to show here is an opportunity, which I haven't found to be really exploited in the whole PLC area. And the opportunity is about providing an automatic way of, say, this equivalence checking, or even better, writing a piece of software which takes a control algorithm written in ladder logic and simplifies it as much as possible. I'm pretty much sure there is lots of money lying on the floor here. Because we know what we are doing. We are doing logic minimization here. There is theory for that, and there are software tools for that. It's just waiting for somebody to create a startup and start doing these kind of things. If you make any money, you can divert a little bit of that back to me for giving you that idea, okay? Okay, so how can we prove that these things are equivalent? Well, we use something like basic logic simplification rules. The first one being identity. Now imagine that you have A, say, is a light, like event. Light is on, okay? What does it mean? Light is on or false? Well, that just means that the light is on, right? So it doesn't depend on the false. What does it mean, A plus 1? Well, how would it look like in the ladder diagram? Well, plus means a parallel route, right? So the first parallel branch has this contact on that. And remember, here we are energizing, say, a lamp. But there is a second parallel branch with just a true value on that. That means there is no switch here which would prohibit the current to flow. This obviously just means that the current will not care about A and it will just energize the coil, right? So A plus 1 is just equal to 1. Okay? A times 0, what does it mean? That you are putting basically a contact here and you put a gap, like a physical gap, and you say, no, you will not flow. Okay? A times 1 is just A, okay, for obvious reasons. Okay? Then we can go further. We can say light is on or light is off. That's always satisfied, right? So that's always the truth value. Light is on and simultaneously light is off cannot be true in deterministic world, well, in any world, besides Schrödinger's cat and these kind of things. So that's obviously just a false value. Then we have something called idempotence, which says that A plus A is A times A is just A. Then in Boolean algebra, we have the standard associativity we know from the classical algebra. We have commutativity, which means we can A times B, if we have here A times B, it's just B times A. It's the same thing, logic-wise. And we have distributivity, as we are used to. Well, maybe not that much, right? Can somebody tell me why this strange relation holds? It doesn't hold in traditional algebra, right? Because just expanding this would be A times A plus A times B plus A times C plus B times C, right? And I'm claiming that it's somehow equal to A plus B times C. How come? Where did this guy go? Where do these guys, where did they go? Okay. So let's apply one of those rules that we already have on the slide. What is A times A? Just A, okay? So let's do it like this. It's A times C plus B times C, okay. Is there possibly any other way we can just write A? Okay, that would be just A multiplied by 1 plus A times B plus A times C plus B times C, okay. Maybe there is something more we can do. Maybe we can take a common. So let's take A, and we are left with 1 plus B plus C plus B times C. What is 1 plus something? That's just 1, right? So it's just A times 1 plus B times C, and A times 1 is just A. So it's like this, okay? So we see that using one of the rules, they lead to this kind of simplification. And these are what might help us to actually simplify this expression to this form. And here I'm going to do it completely manually, but that's what I'm advocating for. Let's write a software tool which does it automatically. I see a huge opportunity in that, okay? So you might look here, say, on the parentheses here, let's take a common. So A is here. B plus not B, so light is on or light is off. That's always satisfied. That's times 1. Times 1 we can just simplify to the left-hand operand. Then we have an A here. We can take a common again. We end up here. Actually, let's expand this whole expression once again. We have this guy here. Notice we have light is on and simultaneously light is off kind of arrangement. So that's obviously 0. Whenever we have 0 in the logic multiplication, the whole stuff is 0. If we have something plus 0, the 0 just goes away. So it's just D times A times D. And since we have D twice here, we have this idempotent stuff which says it's just D times A, right? So this is what we do. Okay? And this is what I advocate for to actually do, because this is what adds value to the overall process of programming the PLCs. Okay, let's go further. The main trouble with PLCs and with this kind of behavior is that the output coil is only energized for as long as this contact is closed. So it's like if you want to have the switch on in this room, somebody would need to stand there and hold the switch pushed, okay, which is of course not something what we want. But it is illustrated here. The device only works as long as the input is closed. Maybe we want this kind of a behavior. Maybe we would like the output to stay energized despite the fact that the contact dropped back to logical 0. Okay? So basically we would like to enable it by this leading edge and then just let it be run. This is where more of these PLC blocks come into play. Instead of those standard coils, we can have something like sticky coils. These are coils which once get energized by some signal, they need another additional signal to de-energize. So as long as this resetting signal does not arrive, the coil stays energized and the output, this binary output, remains enabled. And these blocks are called set and reset blocks. So the set block energizes the coil whenever there is a leading edge in the input signal. The coil stays energized until there is a leading edge in the resetting signal. Okay? So there is a separate set and a reset block to energize and de-energize a coil. And by the way, what happens if two of those events happen simultaneously? What happens then? Well, the program is executed one by one. So this one energizes the coil, but then immediately the other one de-energizes that. Well, I'm oversimplifying here because the program is not directly energizing the coils. It just computes a numerical value, which is stored at this memory address. And only after the whole program is executed, this memory address, the value is taken, and it's written to the physical output where actual energization takes place. But it's the same argument, really, that we are overwriting the value at this memory address, so that's why the output remains off. Of course, if you would switch the ordering of the reset and set blocks, then a different behavior would be obtained. Okay? And these blocks are really very frequently used. Basically, they correspond to control panels where you have a start button and a stop button. So you want your device to work when you push the button and you release it. The bulb, in this case, it stays on until you hit the stop button. Again, it's the event that time instant of your push that de-energizes then the output. Yeah?
Can you please scroll back to the previous slide?
Mm-hmm.
So from this diagram, from the upper one, how do I know that Q 0.2 is the one which energizes I 1?
Okay, good question. PLCs have input and output modules, like physical modules, where you have interface for your sensors and actuators. Basically, you have 8 plugs in there if you have 8, say, analog outputs. Each of those plugs is then directly propagated to these physical addresses. So that's the Q letter in front that describes that this is going to represent the physical outputs of the PLC. So basically, you look at the PLC, and there it's pretty much written that this input connector will be mapped to an address which says Q0.2. Does that answer your question? So it's just a physical mapping between the physical arrangement of the PLC and the internal memory of the PLC. Basically, you have to know that this is the second, no, it's actually the third one, because everything is indexed from 0, right? So Q00 would be the first digital output. Q01 is the second digital output, so this is the third digital output in your kind of rack of input connectors.
So basically, both outputs here are actually the same output.
Exactly.
They have the same
Precisely.
But one is S and the other one is R.
This S means we are energizing the coil, and we are leaving energized. If there would be no ladder inside, it would be this standard coil, which is energized by the leading edge, but is de-energized once the signal, the input condition, drops back to 0. That would be the standard coil. The sticky coil requires these additional blocks, one which energizes that, and the other one which de-energizes.
It means that I really have to pay attention to the names, because here on this diagram, like two S and R thing, they actually correspond to the same coil, right?
Yeah, and not just on this diagram. On PLCs, you have to pay attention to every little detail.
So there may be numerous depictions of the same object.
Definitely, yeah. Spread it all over your program. Yes, this is what makes programming of PLCs so difficult. Okay. And since this kind of combination of the set and reset blocks is so frequently used in practice, we have so-called set reset and reset set flip blocks available, okay, such that we don't always have to put 2 blocks, remember to put the same physical address on top of each other. We only have a single block which combines those 2 together. They are called set reset and reset set for a reason, because they determine which operation takes precedence when both the set as well as the reset condition appear simultaneously. So the set reset block, what it does is, when a set signal is enabled, the output from the block is energized. It stays energized despite the fact that this contact dropped back to 0, and it de-energizes only after this reset condition is activated. We see that the output drops back to 0. If both the setting as well as the resetting signal are enabled, since we have a set reset block, which means set takes precedence, that's why the output here is energized. Okay? With the reset set block is exactly the same, except of this racy period where, in case of both signals being active at the same time, resetting takes precedence, so the output stays off. And reset set blocks are more frequently used in practice because they are kind of considered more safe, like saying, if I want to start my device, I should really make sure that if somebody pushes simultaneously start and a stop button for any reason, that the machine does not start. That's considered safe. rather than the other way around. Yeah.
So is it executed from top to bottom?
It is executed top to bottom, and even if we have like multiple blocks on the same route, I would say, then they are first executed left to right and then top to bottom.
Which means it is the bottom input which takes precedence. Because
bottom input in which sense? Which bottom input? This one?
So in this case it's R. R takes precedence over S1 because it's more to the bottom. Because it's executed after S1.
So this one here determines which of them is placed on top of each other. So internally, in the block, they would be automatically either reset on the top or reset on the bottom, depending on which of those two blocks you take from the library. So they are really, I mean, these details are really handled inside of these set and reset blocks. Okay. Okay. So now it really seems that you are annoyed by this for very good reason, well, two reasons. Okay. I mean, these things are really annoying. I mean, it's the little things you have to care about when you want to get something running on PLC. Remember, here we are still only talking about stupid logic. We didn't even start doing any mathematics, okay? And it's already annoying. And the second thing is I'm close to that deadline for the lunch. So what I suggest is that I break here. You get a decent lunch, you come back, and then I will finish this part, okay? It's not too far away, anyhow. Okay, so just to wrap up that pesky ladder diagrams and finish with them before we move to something marginally more comfortable. So the the ladder diagrams, they are just software version of electric wiring diagrams, but more advanced. So they contain blocks for, say, the sticky coils, timers, and counters. They don't have direct representation in the analog world, but they are very well implemented on this digital platform. And there are actually many more additional blocks available for doing, for instance, comparisons, floating point mass. But if you consider ladder logic to be confusing by this time, and we were only doing very simple logic control, then doing, for instance, floating point mathematics is maybe even more inconvenient than just those simple things. Bottom line is, I mean, we have seen it. I mean, it's such a simple language, and it requires us to think so well ahead that probably we cannot implement anything more complex than some simple logic, maybe PI, PIDs, maybe LQRs, but that's pretty much it. Anyhow, for everybody who is interested in learning exactly what the blocks are, how they are used, I'm referring to the Siemens user guide for one of their PLCs. It's like 700 pages. That's the sad reality which we have to face. And I mean, I think I warned you on a couple of occasions, and I'm going to continue with that warning. PLCs, I mean, that's the most abundant type of hardware, and they have their own limitations, and they are very strict limitations. And however, they have a very wide user base, so if we can do anything, we immediately have the market at our disposal. So let us move to the second graphical programming language, and that's the one we will use in the exercises. And it's called function block diagrams. They do the same thing as the ladder diagrams do. They just look a little bit nicer. Okay? So what we see on the left-hand side are the two ladder logic diagrams, the serial arrangement for the logical multiplications and the parallel arrangement for the summation. And what we have in the function block diagrams, as the name already suggests, is that we have basic building blocks, many of them only taking two operands, where we just connect the inputs into, and then we can take the output from the block. Otherwise, it does the same thing exactly in the same fashion. Okay? So if we take something more complex, it's actually this ladder diagram is translated into this function block diagram. So what we have here is, for instance, when we start from the very back, we have the, which one is it? Okay, no, it's actually this block here. So we take the negation of A1. Here I beg for your precise spot of this tiny little dot, which suggests that the input into the block will first be negated. The message, be careful where you click, because you also want to click here to connect this arrow, so it's kind of like Simulink kind of programming. But if you click just 1 millimeter to the right, you suddenly negate the input, and then you might wonder why your control algorithm exhibits a completely different behavior. But yet again, that's the sad reality of PLC programming. Every click, every typo in your code, I mean, it will not break your code. That's the bad thing about it. The compiler will not kind of warn you, but it will just execute a different logic from that you have designed. So this little dot here and also the one here, they mean negation. So here we are just adding these two binary inputs. Then we are summing these two guys together again with a negation. We are adding this I5 to the mixture, and then we are making a logic multiplication and then propagating it to the output. But otherwise, it's exactly the same as with the ladder diagrams. You might choose your favorite tool. Usually the software tools for PLCs, they support all of these languages, and if you even write the code using one language, you just press a button and it's automatically translated to a different language. However, for the environment that we will use on the exercises, it will only provide this function block diagram programming thing. Okay? So let me show you also 3 examples. And you might say they are very simple ones, but I would say that they exhibit pretty much the typical nature of control algorithms that are implemented on PLCs. So let us consider that we have a tank that we would like to fill out with a pump. And we have one digital input which just switches on and off this pump. So it either operates with a maximum flow rate or with 0 flow rate. We have one digital input which would be some kind of manual operation of that pump. And we would like to operate the pump for as long as the button is pressed. So this is the simplest thing you could think of. I mean, there is no control involved here. So in the ladder diagram, we would just have one contact and the coil. In the function block diagram, it's even simpler than that. I mean, we just directly connect the input to the output, and that's it. Okay, not interesting for us because it's not really control. So let's do some control on that. Let us now have 2 buttons, start button and a stop button for the pump. And we would like to start the pump and let it operate after we have pushed the button and returned it to the standard mode. And then we have the stop button to stop the operation, right? So this is what we have seen in the first part of the lecture. This is what those set reset blocks are about. These are like the control panels for your devices. That means that we take from the library the set reset block, and we connect the starting button to the set signal and the stopping button to the reset signal, and we connect the output directly here. The nice thing about this particular environment that we will use for exercises is we do not need to do memory allocation. Trust me, if we were to do, we would just be doing that for half of the exercises and nothing else. Okay? So here everything luckily is tackled by the platform itself. So this is still some kind of just, I mean, running the pump or not running it. So let's get real control involved. Let us have some kind of a finite state machine to control our device. So we will have 2 thresholds. So we have the lower threshold and the upper threshold. And we would like to start up the pump when the level is below this threshold B. And then we would like the water level to rise above A, at which point the pump should be disabled and the level will again drop back, and then it will be turned back again, and so on. So basically, we just need a very simple finite state machine with 2 states, the on state for the pump and the off state. And we switch to the on state whenever the level, as measured by some analog input sensor, is below this threshold B, and we switch to the off state where the level is above A. So these are very simple control algorithms, and actually from the implementation point of view, what it requires are the blocks for comparing these 2 values. So we need to check the truth value of these 2 conditions, and then we have to have a block which switches between these 2 states. And this can be actually realized rather efficiently. So here we have the comparison blocks. So each block compares the first value to the second one and gives a truth answer. So here we have a 1, 0 output depending on whether this condition here is satisfied. If it is, it will start the pump. And this condition is where the water level is increased above this upper threshold. It's the condition which switches off the pump. And trust me, I mean, majority of the control algorithms that you can find in process industries, they run on using these kind of very simple finite state machines. Of course, then you can have more of these finite like states in the finite state machine, but there are still just these kind of switching controls at the end of the day. So let me show you also how it works, such that you get a teaser of the exercises. Let me switch this here. Hopefully everything will be visible. Okay, so that's the environment that we will use for the exercises. The advantage here is that it's a complete simulation of a PLC. And here I have to warn you, I mean, again, vast majority, if not all of those PLCs, they only support Windows. That's the sad reality. They have arguments for that, and that's what we have to accommodate for. So I'm running it in a virtual machine. So I'm starting the simulation now, and here I can manually operate the input. So you see this little number here, which is kind of like me pretending what's the level in the tank. And the condition said that once it increases above 7, then the pump here should get switched on. Currently it's off. So let me kind of gradually increase the water level. It's at 7. Now it's at, what the hell? Oh, okay, so it's, no, what did I do? You should never do live demos, you know? Never do that. If somebody tells you to do a live demo, do a recording beforehand and then just play that one. Something is really wrong with my simulation. Okay, I will scrap it. I will come back to that on the exercises anyhow. Okay, another type of control, and that one I hope will work. Let's do just proportional control. Okay, so we will consider that again we have this measurement, but this time the measurement will not come from outside world. Since we are in a complete simulation, we will also include a simulation model directly onto the PLC. So I will just be including a nonlinear simulation model with one state. I mean, the accumulation is equal to the difference between the inflow and the outflow. And we would like to regulate the voltage to the pump by a simple P controller, right? And actually, this is like one line in MATLAB we have to write to implement P controller, and another line to implement the mathematical model. Everybody could do that, right? Well, this is how it looks on a PLC, right? So there are a couple of things here. So when we start from the right-hand side, here we have a block which is called formula. It's one of the most advanced, if not the most advanced block of a PLC. It allows you to perform some mathematical formula on 4 inputs to the block. 4 inputs. Think about it. Like you have to sum up 6 numbers. You have to use 2 of these formula blocks. That sounds ridiculous, right? That's what the world of PLC is about. Okay. So luckily, I have designed the example such that it only needs 4 of those inputs. So one of the input, of course, is that when we want to compute the water level at the next sampling instant, we need the current water level. So that's what is stored here. We need the delta, which is here as a constant here. So it's just a number which I can adjust from the graphical user interface. I have the vent constant K here. They all enter into this formula block, and this is how it is written inside. So inside of this block, the inputs are marked as I1 to I4, and you can put like your favorite mathematical formula as long as it has 4, like operates on 4 inputs. And it computes the update of the water level, which is then stored to something which is called a memory flag. So memory flags are just some kind of temporary memory that you can use if you want to read or write some value on multiple occasions, such that I can avoid, because in Simulink we would have a line connecting this block back, like feeding back the value, since we need to compute the state update. So this this kind of breaks the loop of the line and uses temporary memory to store the values. So this is just the mathematical simulation of the plant. Then, of course, we need the P controller. So for the P controller, we need to have the gain multiplying the control error. So the control error is computed here, where we subtract from the reference, which is the first input. We subtract the water level, which is again read from this memory point. We have the control error. We multiply with the gain, and yeah, that's it. So already such a ridiculously simple thing as a P controller, and we see that it requires quite substantial effort. Well, actually, it is not as bad as it sounds, because of course, PLCs, they come with pre-configured PI, PID blocks. So there you just set up the what should the gain be, what should be integral, and the derivative time constant be, and it's really just a single block. So let's hope this works now. Okay, so okay, let us zoom in. So currently the set point is 5, as indicated here, and we see that the regulated output exhibits some offset, which is of course not surprising, because we only use a proportional controller. We can get rid of the offset by using a PI controller, and that's what you will do on the exercises. Oh, okay, now it works. Okay, so you move the set point, it regulates somewhere else. So, okay, at least this thing has worked. Good. So let me finalize the theoretical block, if I may call it like that, by saying that what we have just seen is something, I mean, probably you didn't expect to see this, right? But as I said again on many times, that's simply the reality that we are facing. What we are facing are programmable general purpose controllers which are suited for simple tasks only. And unfortunately, that's the majority of the control hardware. They have severe restrictions, not just on memory and CPU speed. That's what we are all after, like saying simplify everything, compute it fast. But they also have severe limitations on the way how we program those things. And that's probably even more difficult, or more often constrained, rather than just constrained on the memory and the computational power. However, they are ubiquitous, especially in process industries, and they are not going anywhere anytime soon. I mean, this kind of control hardware will stay here for the next 20, 30, if not more years. So the whole message which I wanted to convey to you is the following. I've done my PhD in Zurich with Manfred Murari on explicit model predictive control and this parametric optimization thing and so on. And of course, we also had to have applications, right? The way how we approached that in Zurich was that we bought a FPGA card for, I don't know, 3,000 euros, because we selected it because it was powerful enough to accommodate the algorithm that we wanted to exhibit, right? And everything worked perfectly. Then I came back to Bratislava, and I also asked, like, okay, so what kind of control hardware do we have here for me to exhibit these algorithms on? And well, Miro Fikar, he brought me to the lab and showed me a PLC with 2 kilobytes of memory and told me that's what we have, right? And we are not going to get anything else. And strange thing happened then, that we started to work on theory how to get MPC to run on 2 kilobytes of memory. And then people from the industries approached us because they said, you know, you are one of the very few ones who do this. All the other like scientists, they buy hardware which is good enough for their algorithms, but they don't think about what the practice needs. And the people, they were really appealed by our algorithms, and they accelerated the development even further, because they said for them to replace the control hardware, it's not the price of the replacement of the hardware itself, But then what you need to do is you have to recertify your overall control system because you are suddenly using a new hardware. You have to do a new documentation. You have to do a new training for the people who sell and support their control systems. And they were saying that this cost of changing the hardware and that induced cost is so high that they are reluctant to change the underlying hardware units. So the bottom line being, apparently there is big need in the industry to get new algorithms to run on existing hardware. And one of the existing hardwares that you might encounter are exactly PLCs. Okay? So that's the message for you. And by this, we can conclude the theoretical part of the lectures. Thank you very much. Yeah, Giovanni?
Just one question. So with this software, is it just a simulation environment, or you can also nest the algorithm to any kind of PLC? Because I know that if you have a Siemens, then you have your own software, you have to use that on...
Okay, those languages, they are they are certified in a way that if you can kind of extract the description, say, of the ladder diagram to a text file, and you can get the other PLC to interpret that, there is no loss of information. So they are really compatible. Again, the devil is in the details. How does the particular programming environment store those files? For instance, the environment we will use uses open XML description, so pretty much everybody can take those files and transform it, say for Siemens SIMATIC PLCs. So that is possible. That's also the big strength of PLCs, that everything is standardized, and you can take literally the same program and implement it on hardware of any producer. So it's not that you would be running on some unsupported functions and so on. That's why also the language is so limited, because they have to accommodate for the most common denominator across all platforms.